I will try to be as quickly as possible, as I know I'm the last barrier between now and lunch. I think Simpiwe and I had a very similar point of view when we decided on how to structure our presentation. So I'll talk a little bit about what the problem is that we are facing, the threat, and why we are doing this type of research. And then I'll spend some time on a case study of a protection solution before concluding. Landmines and improvised explosive devices remain a major threat for military vehicles, their occupants, and other assets. If you have a look at the map over here, even though landmines are not being planted, there are still lots of landmines that have been planted in previous conflicts. And you can see that the African continent is still quite prevalent. There's quite a lot of red over there. And as our National Defence Force is working in the African continent, it's important that we have protection against this. Warfare is shifting from conventional to unconventional tactics and weapons. The improvised nature of IEDs make it difficult to predict the terminal effects. I mean, IED stands for improvised, which creates a paradox. We now need to try and predict something that we don't know much about. And for these reasons, traditional methods of protection need to be adapted or new technologies developed. IEDs have become the #1 choice of attack for a number of reasons. They can be remotely detonated, so there's no danger to the insurgent, and this makes it an attractive thing. They're very easy to manufacture. Unexploded ordnance is used to get these explosives. They can use stuff that you can find at home, a can, a pot, and these can all be used to form IEDs. There's a surprise element. They can be hidden in plain sight. One of the most common ways for IEDs is parking a vehicle on the side of the road, filling it with explosives, and then detonating it when a target goes by. So they don't look out of place. There's a lack of countermeasures and protection available for these. There's a massive psychological effect on morale. Your logistics get disrupted, and there's a devastating terminal effect. The picture over here was taken in Africa, and these are just examples of some EFPs that were found before detonation. You can see how crude and rudimentary they are. This is actually a pot filled with explosives. And these are the triggering devices that they use. I'm going to show you a video. That is a buried blast IED. Luckily, in this case, the IED was mistimed and nobody was injured, but you can see how devastating these things can be. I've put the sound off, but in the actual video, you can hear the language in the car. Okay, this slide is also just to highlight how prevalent these IED incidents are. This is based on the African continent. It's a little bit dated, it's a 3-year-old slide, but I just wanted to show you in the top graph. The red represents the number of detonations per month, the yellow represents the number of fines, and the blue represents the number of caches that have been found. And we're looking at an average of about 38 detonations per month in Africa. And then if you look at the casualties, the red is killed and the blue is wounded, and we're looking at about an average of 79 killed per month. So even though the slide is a little bit old, I think that the statistics at the moment is similar, if not worse. These are examples of damage due to IEDs. These were taken in Northern Africa. These are all explosively formed projectiles. You can see how they penetrated the occupant's compartment. This is damage that was due to a blast IED, similar to the video that I showed you. What's very impressive is that even though the damage is pretty bad in this picture, nobody was killed in this particular incident. And there's some South African technology in this vehicle. So before a solution can be devised, the damage mechanisms need to be understood. For research purposes, we've split this into 3 classes: blast, penetrative, and then your dirty bombs or your nuclear, biological, and chemical. In terms of blast, these are usually characterized by quite a large explosive content. You have shock, there's overpressure, there's an impulse transfer, you've got local deformation that can damage things. Biotrauma is very critical. In terms of the biotrauma region, we usually split the injury into 4 different areas. Your primary blast injury is due to your blast wave, your shock wave. These often affect your air-filled organs. Your secondary blast injury is due to fragments that get formed during the blast. Tertiary, this is when your whole body gets displaced. For dismounted soldiers outside the vehicle, the body physically gets moved a distance. Inside a vehicle, you almost propelled off your seat, which is why your seat restraint systems are so important. And then lastly, we've got quaternary blast injuries, and this is due to burns because of the temperature effects. Another issue with blast is that normal, conventional explosives are not being used. Additives are being added. And what this does is it creates enhanced effects, an increased impulse, higher temperatures, a longer duration. And then, of course, there's structural failure. With the second class, which is your penetrative, these are further subdivided into two. Directional, this is when you target a specific area, and here you've got your explosively formed projectiles, which I'll talk more about later, as well as your shaped charges. And then indiscriminate. An example of an indiscriminate one is that pot that I mentioned earlier. You fill that with explosives, you add a couple of nails, and when that gets detonated, all those nails then become fragments that can go over a wide range. The last one is NBC. This is the explosive dispersion of chemical, biological, and nuclear material. At Landwoods, we don't look at this, but I think it's very important just to know and be aware that it is there. Okay, so now we'll get to the case study. The aim for this particular case study was to develop a protection solution to protect against a medium explosively formed projectile, IED threat. Unfortunately, there is no one solution that will fit all the problems. So over here, we've just concentrated on the one size. By medium, I'm talking about 120 mil EFP. This is quite a nice picture that explains the whole EFP process. You're looking at explosive inside a casing, and then a liner, usually copper, on top. And when this gets detonated, the blast ejects the liner starts deforming, and that forms a projectile, and this projectile can pierce through your armor. The rule of thumb is that you can penetrate up to half the diameter of an EFP. So if we're talking 120 mils over here, you're looking at a penetration of 60 mils of armored steel. So to design protection solution, we need to understand the threat, and EFPs are usually characterized in terms of the projectile formed. The three parameters that are most critical would be your mass, your speed, and your shape, because these all combine to give us an idea of what the kinetic energy over a distance is, and then that will tell us what the required protection would be. For research purposes, it's important to have a repeatable threat. IEDs are improvised, no IED is the same. But for us to be able to test a protection solution, we need to make sure that what we are testing is going to be the same each time. And for this reason, we have to develop an EFP surrogate. So we came up with an initial design, and then we modeled it computationally. Kavin mentioned how expensive it is to testing, so we also do quite a lot of computational modeling, where we can get the performance of that projectile to our required parameters as closely as possible. Once we're happy with that, we then manufacture a prototype, do some experimental testing. Experimental testing is against a simple steel plate target. We use high-speed video footage in order to see what is going on, and then we also use specialized diagnostic tools, specifically a flash X-ray. And what this does is it records an X-ray of the projectile during the formation. And what's nice about this is, besides the fact that it's extremely fast, we're looking at projectile speeds of up to 2,000 meters per second. It can also penetrate through the debris cloud. When you're doing explosive testing, there's often a lot of debris, there's a fireball, and we need to be able to see inside of that. This is an example of a flash X-ray of one of the projectiles that was formed. Based on our experimental testing, we then modify or fine-tune the design again, and the whole computational modeling and experimental testing can be an iterative process until we are happy with the solution. The final design is pictured over here, and this was tested as well just to make sure that we were getting repeatable performance. Okay, I'm going to go back to those three parameters, mass, speed, and shape. A good protection solution needs to be able to either break up the projectile, so reduce the mass or change the shape, or slow the projectile down sufficiently enough that it cannot penetrate through the occupant compartment or final target layer. Because different materials react differently to the projectiles, we standardize in terms of the thickness of rolled homogeneous armor that is required to prevent penetration. And we use this as our sort of guideline, so we can calculate what the aerial density of this is and then work backwards on that to say this is what our mass budget and dimension budget is. It would be easy to slap on 60 mils of RHA, but then your vehicle will become so heavy it won't be able to move. So we need to keep these budgets into consideration. I'm being purposely vague about what the actual concept design is. But it was based on research into a number of different fields, such as shock physics, threat-target interactions, material behavior, new materials, etc. We developed concept designs of the panels, and we tested the panels, again using high-speed video footage and flash X-ray, in order to see what the projectile parameters were before and after interaction with the panel to see whether it actually slowed down or broke up the projectile. Again, it was an iterative process between modeling and experimental testing until the final design was achieved. And we then combined panels in different formations in order to form an actual package. These are just pictures of the test setup over here on the individual panels. These are the X-ray cassettes that we use, and the panels are in the middle. And then this is the EFP surrogate. This is the package itself and the X-ray cassette. In conclusion, we've developed an add-on protection package to protect against the medium-sized EFP IED threat, and the case study shows how the research, development, innovation process was followed to reach a solution, or reach a partial solution to a much bigger problem. But of course, let me rather show you videos of this. So the top video is of the EFP surrogate being fired against an unprotected hull, and the bottom video is with the protection package added. You can see it going through not just the first layer, but all the way through on the other side as well. Whereas in the second video, the package stops it. Thank you.